Hello friends, in this video we will see how to convert a sorted linked list to a balanced binary search tree. So a balanced binary search tree is a binary search tree, so it maintains the search property and also the difference between the depth of left and right subtrees. So if there is a node here and we have a subtree here and the maximum depth here is, let's say, 5, then in this part it cannot be more than 6 or less than 4. So difference can be at max 1, and this would be true for all the nodes. That is, for all the nodes you look at left and right subtrees and the difference would not be more than plus minus 1. So for example, we have this sorted list 1 2 3 4 5, and if we convert to a balanced binary search tree, it will be something like this. So if you see what is the depth of left subtree of root node 3, then it's 2. Right side also it's 2. So for 3 it's valid. For 2, left subtree has a depth of 1, right subtree is nil, so it has a depth of 0. So difference is 1. So again the property is valid as 2. Similarly, you can see that it's valid. So at all the 5 nodes it's valid. At 5 also it's 1 and 0. So difference is 1. At 1 both are 0, so difference is 0. Similarly here. So this is a balanced binary search tree. Now let's see how we can convert. What is the algorithm here? So when we are given a list, we have a bunch of values. Let's take a generic case. We have, let's say, n number of values given to us in a form of linked list. This is not an array, so you have to iterate one at a time. So we have many elements and these are sorted, and you see that when we do the in-order traversal of a binary search tree, we get a sorted list. So this is already sorted, so you can think of it as the in-order traversal of the resulting binary search tree which we are trying to build. But this is not a simple binary search tree, it's balanced. So left subtree, all the nodes of left subtree, followed by the root node, followed by all the nodes of right subtree. So this will be the order. So root will lie somewhere in the middle. So if it's odd, it will be exactly in the middle. If it's even, it will be one of these. You can pick one of these. So the algorithm is that we find the middle of the list. So at this point we only know about that the middle node should be root. So we make this as the root, and then we have this remaining elements in the left subtree. So all the L will come here, then root will come here, then all the nodes of right will come here in this list. So now you see that naturally recursion is coming here. We are breaking the problem into a smaller problem. Earlier we had a bigger list which was L plus R1. Now mid we have extracted as the root, and then in the left part we have this list of length L. In the right subtree we have this list of length R. So the same function, whatever function we had written to do this conversion, can be applied on this part and the right part. Now we have a smaller problem. Again here we will find the middle, make this root. So let's take a concrete example. Let's take our original example, 1 2 3 4 5. Let's say 5 elements. Next is null. So in order to find the middle, we all know the slow and fast pointer concept. So we can have a slow and a fast. You can initialize in multiple ways. You can keep both of them in the beginning, then there will be a shift of one element. So let's say slow is initialized here, fast is initialized here, and slow moves by 1 step, fast moves by 2 steps. So when the fast reaches to the end, or one before the end, one before the tail, then we stop. Then slow will be somewhere in the middle, either exact middle or this one. So let's do it. So next slow will come here, fast will come here. So fast we are advancing by 2 steps. Next. Now again slow can come here and fast can come here at the null. Or you can stop here itself. When the next is null, you can stop. Then this slow is at the middle. If it was odd number, then we would not have moved this one. Then the middle was next of slow, or you can have taken this also as the mid. So this way we find the mid. So what time it takes? It takes O of n. If the length of list is n, it takes O of n to find the middle. So this is first step. So after this step, what happens? We make 3 as the root, and we call the same function on 1 and 2, and then we recursively call the same function on 4 and 5 after n steps. In the next steps, we will have this n by 2 elements here. Roughly, I am not writing plus minus 1. This will not change the time complexity. And then n by 2 roughly here. So again, this time the finding the root will take n by 2 times. And similarly here n by 2 times. So for a balanced binary search tree, when this will terminate? When we have single nodes itself, then it will be constant time. And what is the height of a balanced binary search tree? It's log n. So each step we are taking n times. So here n by 2 plus n by 2. Again n. Similarly here n by 4 plus n by 4 plus n by 4 plus n by 4. Again n. And this length is log n. So overall time will be n log n. So the time complexity here is O of n log n. Space, we are not explicitly using any extra space. We will just modify this list itself. So for example, when we find the middle of the list, so we have this 1, 2, 3, 4, 5, and its next is null. So we found out 3 as the middle. We made this as the root, and it's left and right. So right is fine. We will call this on the next of this 3. So it will call on 4 and 5. But if you look at this part, if you simply call this recursive function on this head left part, then this next pointer will think that, so in the list we have only access to header. Using that we step until we reach the end. So this pointer is crucial. You have to disconnect it. You have to make it null. Otherwise it will treat this whole thing as the list and it will go on again and again. So this we will do in the code. So space we will treat it as O1 and time as n log n, and you got the idea how we are doing it. So let's write the code for this in C++, Java and Python. And there is one mistake here, so it should be 109 problem number. I forgot to change it. So now we will write the code. So this is another example. Again, this is sorted and we get a similar structure. So let's take the base case. If the head itself is null, that is list is empty, then nothing to return null pointer. Similarly, if the next of head is null, that is there is just one element, again there is nothing to worry. We will return just a node of a tree, and the structures are different. In a tree we have left, right. In a list we have next. So return new tree node. And what is the constructor? It takes a value as the value of the node, which will be value of this head itself. So these are the base cases. Now let's find the middle. So for that we will have list node slow equal to head and fast is equal to head next. And while fast next fast next is there and fast next is there. Again, you can do it as per your choice. You can stop when the next is null itself, and you can allow it to go to null also. So this check may not be required depending on your use case. It's up to you. You will need to modify the code accordingly. So fast becomes so, or let's write slow first. So now when this loop ends, slow will be at the middle, or in this case we are stopping even when next is null. So slow ideally should be one before middle. Then we have to break this chain. Remember this, otherwise it will treat this whole list as the left part of the list. Then this root node, mid value, and root left equal to the same function on head, but we have disconnected it after slow. So from head till slow, left part. And similarly and finally we return the root. So this is very intuitive. I hope you understand it. Now let's run it. Hopefully there is no error here. So there is error. Null pointer of list node, line 28. If so a null pointer line 28, so fast is head next, so head next is null, but if head next is null, so this should be head next, this case. So if head next is null, we return this. That is one node case. Now let's try it. Now it seems to be correct, so let's submit, and the solution is accepted. Now we will do the same thing in Java. Not much change required here. and the Java solution is also accepted. Now we will do it in Python 3. And the Python solution is also accepted.